In science fiction, black holes are vortexes consuming anything that comes too close. In reality, they're even more confusing. A black hole is not so much a thing, it's really more of a place. A place in the universe where gravity is so intense that basically nothing that enters it can ever leave. Not even light. And if that weren't weird enough, at the boundary of a black hole, called the event horizon, time essentially stops, or appears to. So if you were floating toward the event horizon, a person watching you from a distance would see you slow down and freeze right at the boundary, seemingly stuck there forever. Given that they are so dark, you'd think they'd be impossible to find. Generations of scientists have hunted for them, and over time, we've learned they're actually pretty common throughout the universe. And nearly every large galaxy has a gigantic black hole at its center. So how do we know so much about something we can't see with our own eyes? Let's dive deep into black holes. From GBH in Boston, this is Nova Remix. I'm Caitlin Sachs. Before we can appreciate black hole discoveries, we first need to understand some basics. Like so much in modern physics, it all starts with Einstein and with gravity. Science historian Dr. Peter Galison explains.
Einstein came up with a supremely simple concept, and that is that space and time is bent by the Earth and by the sun and by all the objects in the world. And there are no forces anymore. There's just objects bending space-time and other objects following the straightest line through it.
So let's break this down. What does it even mean for an object to bend space-time? To understand space-time, it helps to understand how gravity really works. We typically think of gravity as a force that pulls on things, almost like a magnet does. But the reality is stranger than that. According to Einstein's general theory of relativity, everything in the universe with mass distorts the geometry of space and time itself. The bigger the mass, the bigger the distortion. So when you throw an apple, and it follows a curved path from your hand back to the ground, what's really happening is that it's following a bend in space-time caused by Earth's gravity. Or if you were floating in outer space and threw the apple, it would just keep going along a straight path until it encountered a bend in space-time from some large object. Having a hard time picturing how this works? Try this. Imagine you and 4 friends pulled a rubber sheet tightly between you. Let's say this sheet represents a simple version of space-time. Now, imagine you place a bowling ball on it. When you do, the rubber stretches under the weight of the bowling ball, just the way the mass in the universe bends space-time. Next, roll a marble from one side of the sheet to the other. If the marble rolls far enough from the bowling ball, it'll just roll straight past. But if it's close enough, the marble's path will curve as it rolls through the part of the sheet bent by the bowling ball. If the marble rolls even closer, it will simply roll into the bowling ball and remain trapped there. That's the way that gravity works. So the next time you look at the moon, just imagine it as a marble rolling along a path bent by the Earth. When Einstein first published his revolutionary theory, he was using mathematics to describe how mass warps space-time to create what we conventionally understand as gravity. Big things influence small things. Einstein hadn't considered the concept of a black hole yet, but someone else would. Journalist Marcia Bartuszak explains.
Karl Schwarzschild was a German astronomer, head of the Potsdam Observatory in Germany, and just weeks after Einstein presented his papers, Schwarzschild quickly got a copy and was mapping the gravitational field around a star.
Schwarzschild wasn't making these calculations from a quiet office somewhere. It was 1915, during World War I, and he was in the German army calculating artillery trajectories, literally from the trenches. He was intrigued by Einstein's theory, and between volleys, he took a deep dive into the equations.
Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly.
But Schwarzschild wasn't done. In his solution to Einstein's equations, he discovered something Einstein himself had not anticipated.
Schwarzschild said, I can calculate this strange distance from a gravitating object that represents a kind of boundary.
Remember, Schwarzschild and Einstein are only working with calculations. They are exploring gravity with mathematics, and Schwarzschild mathematically pushes Einstein's equations to the limits. On paper, he concentrates a large mass, like the mass of a large star, into a single point. Then he calculates how crunching that immense mass into a tiny space would bend spacetime, and he finds something astonishing.
As he, through his mathematics, aimed particles of light or matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped.
A black hole. Schwarzschild had mathematically discovered that a very dense concentration of mass will bend spacetime to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light. Remember that rubber sheet example? A black hole would stretch the fabric so much that it would essentially never stop stretching. It's like the gravity would just keep pulling and pulling and pulling and pulling the hole deeper and deeper without end, making that extreme gravity well into a hole in the fabric of space-time itself. An utterly black hole.
It's like those roach motels. You can check in, but you can't check out. Once you go across that boundary, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time.
Everything near it goes in, nothing comes out. That's the basics of black holes. But just because Schwarzschild proved it on paper doesn't mean that the idea of black holes was widely accepted, or that they even existed. After all, scientists at the time didn't see them. Even Einstein was skeptical, and it was his theory that led to the idea of black holes in the first place. Astrophysicist Dr. Priyamvada Natarajan explains.
Einstein and all the sort of, preeminent astrophysicists in the 1930s or 1950s did not believe that they were actually real. It remained a solution, a mathematical enigma for a very long time. So it took a long time for people to even start looking for them.
The idea that so much mass could ever be crunched down to a point didn't make sense. Realistically, what object could ever bend spacetime so that nothing escaped it? As scientists understood it at the time, stars and nebulae were certainly large, but they weren't dense enough to create black holes. And if they were, we wouldn't be able to see them because no light could escape them. As science progressed and the world witnessed the atomic bomb and the rise of nuclear science, we would find a new clue, coming from our understanding of stars. Stars are supported by the power of nuclear fusion. That's when the nuclei of two or more atoms merge together, like two hydrogen atoms merging to create a helium atom. It takes a lot of pressure to force those atoms together, but when they join, that merging releases a lot of energy and light.
Stars are stable because you have an outward moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity.
Dr. Niyamara is explaining how stable stars behave. But while stars may seem eternal to us, they do die.
Stars are in many ways similar to living creatures. Like humans, they have life cycles. The life cycle of a star really depends on its mass. The mass of a star determines what's going to happen after it finishes burning its hydrogen fuel.
Now, things can go one of two ways. If a star is smaller, like our sun, it will burn out its hydrogen fuel and then condense into a white dwarf, just dense remnants that are no longer undergoing fusion. However, if a star is larger and more massive, gravity keeps pulling atoms closer together until they fuse into heavier and heavier atoms, all the way up to iron. And that's when things get interesting, as Dr. Eilat Glickman explains.
Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out, and gravity wins. And so the entire star collapses.
Collapse doesn't do it justice. First, the thing implodes. Then, it often explodes spectacularly, going supernova. This means it's game over for fusion. And without that outward pressure, the remaining core keeps collapsing down. If the mass is great enough, this squashes everything into an infinitesimal point, a so-called singularity. And that single point would have such extreme gravity that there would be an area around it where no light, sound, or anything could escape. Voila, a black hole. It sounds impossible, but remember, we are talking about a star's mass. It would take 330,000 Earths to match the mass of our sun. If the sun were condensed into a single point, you can imagine some extreme behavior in spacetime. But even our sun isn't large enough to form a black hole. According to Natarajan, black holes come from even larger stars, about 20 times the mass of our sun. And there's plenty of them.
So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone.
But remember, all this work was theoretical. No one had actually detected a black hole. Not surprising, given that black holes are invisible, right? Well, nuclear fusion has an invisible byproduct: X-rays.
X-rays come from things which are at temperatures of millions of degrees, even tens of millions.
In 1970, Dr. Paul Merton was a young astronomer trying to secure his next job. By that time, scientists had discovered that space is filled with X-rays, and Merton decided to center his research on this new frontier of astronomy. Eventually, he settled on a particular problem. Compared to typical optical telescopes, X-ray telescopes could only see X-rays coming from a general region, which made it difficult to pinpoint the source of an X-ray signal. But Merton had a clever idea. What if the hidden X-ray source and a visible star were orbiting around each other?
I thought that maybe there was a kind of a star system in which there was a star, one ordinary star that made light, and then there was another star nearby that made X-rays.
Merton found what he was looking for. The constellation Cygnus had been identified as a source of X-rays. Looking at stars in that direction, Merton found one that seemed to be wobbling back and forth. That likely meant that there was an invisible object orbiting around it. After carefully observing the star's movements, Merton was able to estimate the mass of the mystery companion. We now know it was about 21 times the mass of our sun.
When I'd finished writing it all out, I sat back and thought, it's a black hole.
That mass calculation was key. Anything that massive that wasn't a shining star just had to be a black hole. They called it Cygnus X1. But at the time, it was a huge claim. And there were plenty of skeptics. It would take 20 more years for more precise measurements to be made, confirming the mass of Cygnus X1 and officially putting the first black hole in the books. But Cygnus X1 was only the beginning. In 1994, scientists had peered into the center of our galaxy to see what, if anything, was at its center. Some scientists believed activity there might indicate a large mass affecting the movements of other stars. Could it be another black hole? In the mid-90s, scientists like Dr. Andrea Ghez and Dr. Reinhard Genzel were tracking the movement of individual stars near the center of our galaxy. And as Ghez recalls, there was a lot of activity.
These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. They're really hauling.
To move that fast, the stars must be orbiting something extremely massive. Like Merton, Ghez and Genzel were able to infer the mass of the invisible object by the star's motion.
The mass that we infer is 4 million times the mass of the sun. That is the proof of a black hole. In fact, this is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe.
Supermassive black holes. Black holes that aren't just 10 times the mass of our sun, but hundreds of thousands or millions or even billions of times more massive. This black hole, now known as Sagittarius A star, was 4 million times the mass of our sun, And it was right in the center of our galaxy. If something so massive was at the center of our galaxy, what about the other galaxies? Nova and Nova Remix are supported by Carlisle Companies, a manufacturer of innovative building envelope systems. With buildings responsible for over a third of total energy use and energy demand on the rise, Carlisle's mission is to meet the challenge head-on. Carlisle's advanced, energy-efficient, and labor-saving solutions can help reduce strain on the grid. Operating nearly 100 manufacturing facilities across North America, Carlisle is dedicated to helping the transition to a smarter, more sustainable future. Learn more at carlisle.com. Nova and Nova Remix are sponsored by Viking Cruises. Ocean voyages, expeditions, river journeys, Viking is dedicated to bringing travelers closer to the destination, offering a small ship experience and a shore excursion in every port. Learn more at viking.com.
Are there black holes at the centers of galaxies? If they are, how common are they? We simply didn't know.
That's astrophysicist Dr. Todd Lauer, and he joined a team of scientists to answer this question. But he would need the help of another innovation, the Hubble Space Telescope.
Step one, we take a picture of a galaxy with the Hubble Space Telescope. It shows us where the stars in the galaxy are. It tells us its structure and exquisite resolution. The second step, where the real work begins, is to try to model the observations. And we actually do that by building models of galaxies in the computer.
This modeling was known as Schwarzschild's method, named after Dr. Martin Schwarzschild, son of, Carl Schwarzschild. Using observations from the Hubble Space Telescope, Lauer's team would model a galaxy in a computer, and then through trial and error, they would adjust the masses and velocities in the model to see if the adjustments affected the model's alignment with observation. Lauer explains.
And we say, let's try a star here, let's try one over here, let's have it go around this way, let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars can orbit in this galaxy. Success is when observations of the model match the observations taken with the Hubble Space Telescope. We try it again and again and again, all with no black hole yet, and say, gee, we really can't get the observations explained by the model. Almost always, we have to put in a black hole at the center. We can't match the observations without a black hole in the model.
To make the models and the observations of the orbiting stars match, Lauer and team had to add a mass at the center of the galaxies so large, it had to be a supermassive black hole. After that, almost every time scientists go looking for a supermassive at the center of other large galaxies, they find one. There may be a supermassive black hole at the center of every large galaxy. And that created another mystery. Where did all of these supermassives come from?
For the stellar mass black holes, people thought about them from a theoretical perspective, and then we found them observationally. The supermassive black holes, the story has been inverted. We actually found evidence of them observationally first, and now we're working on the theory of how did these things come into being.
We already know that stars can collapse to create ordinary or stellar black holes, but supermassives are much, much larger. Remember, Cygnus X1 is only 21 times the mass of our Sun. The supermassive in the middle of the Milky Way is 4 million times the mass of our Sun. And there are others tens of billion times the mass of our Sun. Could these come from a collapsed star? It seems unlikely because we've never observed any star nearly that big. You might guess that supermassives come from black holes that simply increase their mass by absorbing enough material. In fact, when a black hole eats, it's quite a show. Up until now, we've described black holes as invisible, and they are. Not even light escapes their event horizon. But just beyond that, matter swirls around the black hole at extreme velocity, generating heat and light. This swirling field is known as an accretion disk, and it's the telltale sign of a growing black hole. But this feeding frenzy has a limit.
Light has a pressure. So photons can impart a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit to how fast you can feed a black hole before its own luminosity quenches its own growth.
The light bursting from an accretion disk will actually work against the black hole's gravitational pull. We don't usually realize it, but photons of light exert a pressure. In this case, light from the accretion disk is exerting an outward force that is limiting the gravitational pull of the black hole. This means that there is an ultimate limit to how fast a black hole can grow. And since we know roughly when the universe began, we know they haven't had enough time to simply grow this big. The supermassives would need some kind of head start.
The problem is still time itself. How do you grow them to 1 billion times the mass of the sun? What are the conditions that you need for that kind of growth? If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growing problem is not as acute.
So, how did supermassives get this head start? The answer might be to create a black hole from an immense cloud of gas, a process called direct collapse.
The denser clouds will start to collapse under their own gravity. And as they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments.
Typically, those fragments continue to collapse until hydrogen atoms fuse, nuclear fusion begins, and stars are born. But what if a gas cloud collapses without ever forming stars?
We realize that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole. You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the sun, and that they form from the get-go with that mass.
Supermassives might get their head start from large amounts of gas that collapse directly into a black hole, rather than a star. But that still doesn't explain what they are doing right in the center of most galaxies. Scientists notice that larger galaxies have larger supermassives at their center. Could they be related?
It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process, and that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock sync.
When a black hole is growing, a tremendous amount of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas, and gas that's too warm will not form stars anymore. And so one way that a growing black hole can influence its host galaxy is by quenching the star formation.
Galaxies grow by forming new stars. New stars come from gas that's cold enough to condense and collapse together. The heat from a growing black hole makes it impossible for new stars to form, because the nearby gas is too hot. In effect, the growth of the supermassive determines whether its host galaxy grows or stagnates.
They have a kind of eating phase and then a quiescent phase. So they seem to be involved with the formation of the galaxy in that way, and then stabilizing of the galaxy at the same time.
By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically, how much power the galaxy gets and at what time as it assembles seems to be dictated by the central black hole. So they might well be the key players in the universe.
It is amazing to think that supermassive black holes might be a driving force behind our universe. And there is still so much more to learn from black holes. The key to that will be finding new ways to observe them. For instance, in 2015, a pair of observation stations called LIGO detected a gravitational wave, a signal from the warping of spacetime itself, which was generated from the collision of two black holes. And in 2019, the Event Horizon Telescope, a collection of radio telescopes from around the world, took the first picture of a black hole. Then in 2021, we launched the James Webb Space Telescope. It's able to study a black hole's accretion disk and particles heated by the black hole's gravitational pull. Thanks to innovations like these, there's no telling what we might learn about our universe tomorrow. This has been an episode of Nova Remix. Subscribe for more episodes and drop us a comment with your thoughts or questions wherever you get your podcasts. We promise they won't fall into a black hole. And if you want to see some amazing black hole imagery and learn more about black holes, check out the documentary Black Hole Apocalypse on Nova's website, YouTube channel, and the PBS app. Nova Remix is a series from GBH and Nova, and it's distributed by PRX. Executive producers are Julia Court and Chris Schmidt, and Senior Director of Digital Media is Nadia Pechek-Rawls. Devin Maverick Robbins is Managing Producer of Podcasts for GBH. This episode was produced by Chris Neighbors with sound design by David Porter. I'm Caitlin Sachs.